case study. This case study is about two very long arch bridges located in southern Spain, okay? Almonte and El Tajo. This is a joint collaboration between Spanish firm devoted or dedicated to low test in general. Another Spanish firm, the first one is called Geosisa, the second one is called Geoson. They are specialized in INSAR, ground-based radars. And then academia, UCC, in which we had a common project together. And first of all, I would like to put some context of this arches, these bridges. The assets belong to high-speed railway networks, which is under construction, almost finished, and that will link Madrid with the border to Portugal, here in Spain. That's the whole line. And we will focus specifically on a segment of that line between two cities called Plasencia and Cáceres. Okay, so let's just put the focus there. And in that segment only, maybe 40 or 50 bridges are already, okay? Typical bridges like simply supported beams, okay? We perform load tests with those beams. Or repetitive underpasses, like this one, Colbridge. Or more complex continuous beams, okay? You can see here instead one of the continuous beams we analyzed here. But you can see now there are two big depressions. There is a big river, El Tajo, and there is a big reservoir. So the high-speed railway network, in order to keep the alignment, to keep slopes and so forth, of course, we needed some assets that are as impressive as you can see here. This El Tajo Viario, 304 meters span, designed by Spanish firm Carlos Fernández Casado. And here we have Almonte, 284 meters, designed by Arena, Spanish firm. So those assets belong to that line, because I want to put the context first. Why? Since in that project of performing load tests, systematic load tests of all of these bridges, many of them were possible to just do the load test using regular traditional equipment. Okay. Even in this one, this is El Tajo. This is the day we performed the load test in El Tajo, the approaching spans. So even in these approaching spans, it was possible for some cases to just do regular load tests using wired strain gauges and accelerometers or LVDTs for deflection, since everything was accessible. Okay? That was possible. But of course, for some cases, this was not possible. So that's when we needed some extra asteroids from the measuring perspective. Okay? Here we don't have a fixed position. Really do reference the measurement to something fixed. And then it's when, of course, topography comes to our mind in general, even classic topography, of measuring from the ground, from a fixed position, the movement in others. Okay? So remote sensing techniques were considered as a possibility. In this case, the remote sensing technique is interferometric synthetic aperture radar, INSAR. Okay, now we refer to INSAR, interferometric synthetic aperture. So this word synthetic aperture we'll explain later. What is this? But it's mainly, it can be this technique, remote sensing technique, spaceborne, okay, from the airplanes or even satellites, in which two images or two infrared thermography or two radar sequence of data gathering are taken, okay? And that can be spaceborne, but that can also be ground-based, okay? Similar principle, it's two sequences that are taken, in this case from radio signals. So this was the option taken by the whole project, okay, in the line, for those cases in which traditional equipment was not possible. Okay. Here we can see a little bit of perspective of the day the load test was performed. You can see now a little bit of zoom out, just to have a perspective, and doing the red insert measurements. So this is unwanted. This is the second, the 384 meters. And for this measurement, there was a need of putting reflectometers, installing reflectometers in key points of arches, okay, in order to get perfect or almost perfect signals from that. Those points, which were of interest, of course, we're talking about the points, key points in the key of the arch, and you have also things happening, things being measured at the time. In this case, this is not the radar we used that day. This is another one, but the principle I want just to show that these two images that can be understood more clearly from the space, in this case from the ground. This radar is moving in the ray length, so those images are taken from one side to the other of the ray. Okay, it's one taken, not only images. I'm talking about data gathering, okay, which is radio signals. But so it is taken from this distance, so which generates like a triangle between the reflectometer and the two ends of that ray. So we perform. The routine load test, okay, this routine load test, which were static for several hypotheses, okay. This hypothesis you can see in the picture is the non-symmetric hypothesis. The arch is loaded on the left part only, okay, one of them. We also have symmetric and alternate, and as you of course can imagine, but this is only one of them, okay, static. Dynamic, in this case, this is a Tahoe. So the locomotive here is smaller compared to the charge in the static load, static test. And in this case, well, several speeds, different speeds for the load dynamics test. And so the methodology is quite simple. The challenge was more the geometry of the asset, but the methodology was a routine test, was like static, several load hypothesis in Tahoe and Almonte, and dynamic, several speed levels in Tahoe and Almonte. That's not really different from any other routine test. So the first thing we needed to do was the identification of those reflectometers, okay, to make sure that these are the key points that are gathered during the how to identify in the software, okay, provided by also the INSAR ground-based radar, in which once it is understood, okay, which are the points and where are they, there are comparisons between specific reflectometers that are reachable by traditional topography total station. Let's say some of them are traditional and they are identified. Here we can see one of the results of the static load test, in which span 7, 8, and 9 were loaded in Almonte Viaduct. So the stepwise nature of this plot, it's because there was one train coming, then another train coming, and another train coming, so it's stepwise. Oh, someone is doing something wrong. So this is stepwise because the trains were coming sequentially and then going away sequentially. That's the nature of it. That's Almonte. In the dynamic test in Almonte, we can see the sampling rate in dynamic test for the radar is quite high. It's like up to 100 hertz, I think. It can perform better, but that one was done in this case. So you can see the movement of a specific reflectometer while that dynamic locomotive is just passing through. And then, of course, the same application. There is the frequency domain results, in which identification of frequencies according to the numerical model and compare. I must mention here that I am not showing anything related to the numerical model, okay, that exists, of course, since it was administration paid to the same company that developed the project of the arch, so they were in charge of their own arch, big finite element model. So it is, in this presentation, we are not like in contact with this other company, and we cannot show, of course, results about it, okay? But of course it was done because it was a routine load test. For El Tajo, so we have similar results. We have the stepwise static load test in which load goes sequentially coming into the spans and then sequentially going away. We have also the movement of reflectometers while that value was, this locomotive was passing. You cannot see it here very well, but this number here is 2 figures, okay, which is a lot of load on the top, static load. And in this case, you can see that's only 1 figure because it was a smaller locomotive, okay? That's why maybe it's no one. You can detect this anomaly, but it's not comparable loads, okay? And then, of course, frequency domain again, which has been for us a very, very nice and big engineering challenge, but ground-based INSAR is not, I think it's proved both accurate and practical for this challenge, okay? Because it's access from the ground to the asset. Both static and dynamic tests were successfully performed in El Monte, 384 meters, and El Tajo, 224 meters, which are Spanish icons today, okay? You can imagine that these bridges are very darlings, okay, in engineering words. And, okay, a little more technical conclusion, the deployment of tests include reflectometers that provide proper and safe installation, because there was even climbing needs, all safety related. And remote sensing techniques represent one practical option for long span bridges and load testing in routine. I finished my presentation showing a little bit of the principles so that the signals are being emitted from the ground, and the reflectometers are being understood from the ground as well. And I also invite you to see what we also did from the perspective of digital twins and load tests. This is Thursday, 2 o'clock, after school, in another section called Emerging Digital Technologies, just to link this presentation with that other, which is more related to the other bridge, not the arches, but the smaller underclass, okay? But it's about digital twins, okay? So thank you very much for listening.
Thank you very much for perfect timing. Do we have any questions? Maybe first.
Did you put a reflector the same place that you put the LVDT?
No, in that case, no LVDTs. It was not possible to put LVDTs.
Oh yeah, but do you know where you did put the LVDTs? Did you put the reflector there to check the results?
The LVDTs at the beginning were installed
Back at the start of the bridge, in the,
in the approach
span.
spans. In the approach spans, accessible.
But to validate the other one, did you
It was validated with the topography, with the total station, not with this LVDT in this case, because the arch was quite far away, so the locomotives were far away.
on the other side?
Yeah, on the other side.
Oh.
Yeah.
Okay, great presentation, thank you. Did you investigate how the angle with which your, what is it called, INSAR, the angle that it was oriented relative to the target? So did you, like, how acute the angle is and how?
Yeah, this is, in general, the phase angle of the INSAR is one of the main raw material. It's the phase angle and the time. Actually, we're measuring time and phase angle.
Okay.
And it is then transformed into millimeters.
Yeah.
Which we understand, but the original raw data is of course related to the angle. It's assessed and it's investigated. But it's investigated in the practical perspective, like calibrating and everything is okay for performing the routine load test, not really research. But
Okay.
okay.
Yeah, I'm just curious how
Yeah.
much that influenced the resolution of your results.
It's soft millimeter.
Okay.
Yeah.
Okay. Is your goal ever to go? I know notice, is it possible at some point you're gonna try to do something without having to put reflectometers on a bridge? Is there some way that you'd be able to assess response using the INSAR approach without having to put any targets?
I guess that with targets or with less accuracy,
Yeah.
without
any
maintenance, yeah, I guess, but those guarantee that the purpose of it, which is the load test, is
Right.
as accurate as.
Right. Okay, thank you.
Any other question? I think the topic is extremely interesting and extremely difficult to measure displacements of a few millimeters from the distance of a few hundred meters of an arch of 300 meters long.
Yeah.
I have also some experience with the same device, with measuring of displacement of an arch of a masonry arch of 10 meters span, and it was just located a few meters away from the arch, and it was so difficult. However, the displacements were less than 1 millimeter.
Yeah.
However, I'm also impressed that here you have just a few millimeters displacement in such a huge arch.
It's quite stiff, it's quite stiff arch, and the foundations are in rock, so it's, well, but it's, as I mentioned, those are beautiful arches, very slender. They seem to be very slender, but they are quite massive.
At the beginning, I wanted to ask also the same question as was asked by the lady about the verification of your results by other methods. But you think the total stations could get this kind
Some
of
of them were at the reach of the total station, and not all. Otherwise, you use total station.
But can a total station go sub-millimeter from that distance?
Sorry.
Can it go sub-millimeter from that distance, the total
Yeah,
station?
that's also
Yeah,
suspicious.
yeah. But not the whole distance.
Yeah.
Only those which are like.
It would be
slow.
good to do it with the LVDT. You know, to,
Yeah, that was the challenge. Actually, the problem here is that we cannot do it with LVDT.
oh, no, but I mean, come back to your LVDT point and put an extra reflector.
Yeah.
So we've done it on, bridges in Northern Ireland, and but not with, we did it with just vision based, so with the camera, and no targets. We then caught back to an LVDT
Yeah.
to validate it that way. But I mean, the bridge wasn't that big.
Perhaps I have a comment here. We have tested the method also and compared with LVDTs, and it works.
Okay.
It's really accurate. I mean, we were impressed. We didn't
It's
believe
pretty
it.
good.
We didn't believe it in the beginning, but it was really accurate.